but they don't have to, yeah, legal moves, but they don't have to be smart legal moves. Here we go. It's going to happen. All right. So here's a version of a tic-tac-toe game. So you can choose whether the user is going to be X or O. You can choose who goes first. So I'll say computer goes first. Or not. I have no buttons. Okay, we'll let the user go first. It's thinking about things. If you can crash my computer in the process. No.
Delete all data.
Yeah. All your base are belong to us.
Huh. So that's what it needs to look like.
So this would be a good example of about 50 points out of 100. So, because you've got the basic graphic elements displayed, but no gameplay. So I put that up as an example of that.
I think you go first.
All right, so it's working now for some reason. All right, so you click in a square, make your move. The computer makes its move. You click somewhere else.
Oh.
You click somewhere else. And you click somewhere else. Hey, and the game won. All right, so it tells me the computer won, and it keeps track of how many games have been won. So I'm going to switch to O because the O's are bigger. I'm going to let the computer go first. So I hit start, computer makes a move, right? You can't go in that square. You can't click outside. So you make a move somewhere. And well, I'm going to block them up. The computer won anyway. And once the game is over, you can't keep clicking on moves, right? So you don't necessarily have to print messages here, but you don't want to let the person just like keep filling in moves and claim a win. So the computer has won 2 games, so there's my game, and so on and so forth. And then when you're done, you can just surrender, and that exits. But lots of flexibility, right? But the important part is there's a way for the user and the computer to take turns playing moves. And that interaction can be confusing when you're trying to code it. What you might be tempted to do is write some kind of loop. So, not this. So, choose CPU's move, paint, wait for user's move, paint. Right, the sort of first way you might think to do this is to make a big while loop. And the top of the while loop, if the computer is going first, the computer figures out where to put its mark, updates the data structures, calls repaint, and then waits for the user to click. And since we know we get a mouse event when the user clicks, you might set a flag in that event routine, and here you might wait for that flag to get set in some kind of while loop. And then when it's set, you go ahead and you update the data structures, paint the user's move, go back to the top. That's not the approach that's going to work though, okay? In particular, if you're sitting inside some kind of while loop in here, and the user clicks on a square, you're probably not going to see that event. Okay, those events happen when your program exits and the system looks like it's sitting idle. There's something in the background, there's a thread that's basically hanging out waiting for events. But this is like being inside an interrupt routine, right? Where other interrupts can't occur if you've done 270. So you really want to do something like this. So set up stuff and return. And then on a mouse click, which is when the user is making a move, right? Update state, paint, choose CPUs, move, update state, paint, and then return. Right, so most of the time your code is not, the code that you've written in here is not running, right? It runs when an event occurs, you do what you need to do, and you get right out. And then the painting will take place, and when somebody clicks again, you'll go ahead and you'll come into this code and run it again. And a first thing you can do is just make something that lets you click and draw an X or an O, right? O's are a little easier maybe. Just get that working. That takes care of setting up the frame, setting up the action listener, and so on. And then just make something that, I don't know, has the computer move in the square next to you or something, right? So that after you click, you draw the square that you clicked in, and then have the code make a mark in another spot in the board, and then return and make sure you can click multiple times and that it keeps doing what it's supposed to do. That'll tell you you've got this basic kind of flow right. And then you start adding the details for actually doing the gameplay. Other questions? Lab 3 okay? Seems like a lot of people.
You don't need to explain the circuit for lab 3, right?
The circuit's just an LED, right?
Yeah.
But you need to explain your code,
Yeah.
right? And I want to see a flowchart or pseudocode or something that explains how your two threads interact with each other.
Oh,
Okay?
it could be either?
So what? Either pseudocode or a flowchart.
Well, okay.
Yeah. Flowcharts are, well, I mean, you can do either one. But basically the idea is you've got two threads. So a main thread and a blinker thread, or whatever you decide to call them. And each of these is a loop, right? So just spell out what they do and describe in some way how you communicate from one to the other. Right, it's a pretty simple mechanism for Lab 3. And make sure you put your code in your lab. All right, well, let's start talking about some of the built-in classes that implement data structures that we've talked about in 222, things like lists and hashes and good stuff like that. So let me close this. So first thing I want to talk about is linked lists. And there's numerous versions of linked lists. But the two I want to talk about are LinkedList and ArrayList. And these are both implementations of linked lists that we've worked with before. So LinkedList and ArrayList. And we want to keep in mind this idea of abstract data types. So we know what a list is, right? It's a collection of nodes where each node points to a node that comes after it. We have some way of getting to the first node. We have some way of following nodes. We have ways of searching for nodes, adding nodes, possibly in the middle of the list, and removing nodes from the list. Okay, a linked list is not a collection of pairs of data and pointers. It is not a collection of array elements where every other element is an index to the next element in the list. Okay, those are not part of an abstract linked list. It's just this collection of things that we can do a few basic operations on. But how it's implemented can vary depending on where you get this list from, right? And so a linked list and an array list are two implementations, two classes that have, in some ways, different implementations. So a linked list is actually implemented as a doubly linked list. Thank you. So a linked list is actually implemented as a doubly linked list. Does that ever show itself to the user other than performance? Right? Do you need to know if the list is doubly linked or singly linked or circular or not circular? Doesn't affect how you add, how you search, how you remove. It will affect the performance. It certainly affects how much memory it takes and all these other details. But to the user, that's a detail that's completely hidden from you. Okay, so we have this information hiding concept, kind of a firewall. User code, client code, main program, you are on one side of that firewall. Implementation of the list is on the other. Okay, your interface of the list is through these methods that constitute an abstract linked list. So linked lists are doubly linked. These are very fast for doing add and delete. Not quite as fast for doing search. An array list is very fast for reading data from the list. Not a difference you're going to notice on a day-to-day basis, but you can look online and you can see side-by-side comparisons in order of complexity, best case, average case, and so on. But from the user perspective, they're going to feel very similar to you. So we can construct a linked list with just an empty constructor. We can construct an array list the same way. So an array list, we can add elements, and we add to the end of the list. We can also add at a particular location. So think arrays, right? So there's a notion of an index. We can take a collection of elements and say add all of these, starting at some particular location. We can get rid of all the elements. We can search for an object. We can retrieve an object, and so on and so forth. Linked lists, similar. We can add to the end of the list. We can add an index. We can add to the beginning of the list. We can clear the elements in the list, and so on and so forth. So which one you want to use is dependent on what exactly you're trying to do and if there's differences in the methods that are available. But they're both basically linked lists. So when you look at the documentation for this, let's pick on an array list. A few things to note. First of all, an array list is actually an abstract list, which is actually an abstract collection, which is, of course, an object.
What's the little e suffix?
That's coming next. A linked list is an abstract sequential list, which is an abstract list, which is an abstract collection, which is an object. So there's this type parameter e, the type of elements held in this collection. So this is an example of a generic. Because a linked list of integers, of strings, of rectangles, right? The code is basically the same. The only difference is you're manipulating these objects of different types. But to insert them, to search for them, to remove them, the code is identical. So there's a single class, linked list for example, but when we construct a linked list, we have to say what type of objects are we going to put into this list. So here's the notion we're generally going to use. We could say linked list, and then angle bracket and the type of thing we want to store. For example, rectangles. And so this becomes basically a type of variable. Okay, it's a class name, but it's augmented by the type of thing you're putting in here. So we can have a linked list of rectangles called myList equals new linked list, and you have to specify this when you construct also. So new linked list of rectangles, and we can construct without any arguments. So that would be how we construct a linked list of rectangles. If we want strings, we could use string here. If we want integers, we could use integer uppercase I here, or doubles, or any other type of object.
You can actually just not put that and it'll compile, but you'll get a warning.
You'll get a warning.
Because you can't guarantee the safety of the code.
Yeah, and I guess it'll just use objects. I'm not sure. All right, so that constructs a list. And then we can manipulate it in the usual way. We can add things to it, search for things, and so on and so forth. Oh, let me ask, is there anybody in here who is still having problems getting Window Builder to work on their laptop? You try to open a JFrame and it complains about can't open the wizard, org.eclipse, blah, blah, blah. Not happening to anyone here. It was 3 or 4 people in the other section. So if you're having problems with that, upgrading to Photon seemed to fix it, at least under Windows. Don't know about on Mac. So let's make a linked list. Oh, come on. So let's add some things to our list. All right, so we'll add 5 things to our linked list. We got the word hello in there twice. That's not a problem. It's just a list. Doesn't care what you put in there. So let's retrieve elements from the list. So one way to do this is to look at the size of the list. Okay, so this will tell us how many things are in there. And then we can get the element at a given index. Alright, so myList.size, the number of things in the list. For each of those, from 0 up to that -1, we'll just use the get method on the linked list and print out whatever element we have. And This isn't terribly startling. It just gives us the elements back in the same order that we inserted them.
I found there was a shortcut for that, not a shortcut, but like a shorthand
Mm-hmm.
for that for loop, because I was trying to do a for each loop. And
Like
it's
for each.
They don't have for each loops in Java, but they have something that looks like very similar.
Where you say, well, it's in this collection.
Well, you just don't use the words each. You just have for, and then I think it's like the item colon the list,
Mhm.
something like that.
Okay.
I'm looking at it. I don't quite remember what it's.
Another option is to use an iterator. So iterators, I think we touched on them a little in 222. A lot of these collections, lists, hashes, things like that, will give you an iterator. So we can say list iterator, and it'll return a list iterator, which is its own class, and mainly has a pair of methods, has, next, and next. Okay, just like with scanners. So once we have a list iterator, we can say has next, and it will tell us if there's anything else that this iterator wants to tell us. And if there is, we can say list iterator.next, and it will give us the next thing that it has in its collection of things that it's serving up to us. So an iterator is kind of a tool. You construct one, and it has access to all the things in your collection. And every time you say next, it'll give you another item from that collection. And when it's given you everything and you say has next, it'll come back false. Okay, so it's a way to get through, and we don't really need to do that with a linked list because we have a way to say give me the first element, the second element, and so on. But with things like hashes, which we're coming to next, there's no inherent ordering to these. We can't say give me hash element 5. And if we don't know what the keys are on a hash, we can't go through all the keys in order, so we use an iterator typically. So we can use that as follows. So this will give us a list iterator, and list iterators are generic. So we need to specify what kind of thing we want it to return. So here it's going to return strings. And then we can say, well, li.hasNext. So you get exactly the same results in the end, but it's in some ways a more natural way to pull things out of a collection.
I don't remember what it was. It's like for the for each, you just don't say each, and instead saying in, you use a colon. So it's like for string I colon list.
Okay, let's do that.
And internally, that just uses the iterator.
Oh, does it?
It's just its way of saying the same thing.
But you can't, like, use remove. So that's the downside we see as a shorthand.
They say a string word in second for each loop. Yeah. For each string.
For or for each?
Just for, and
Just
then
Why would you just say string word if you've already got the word
Declared as a string.
declared?
I don't know if that would work.
That's what the int I is about. You can have an integer
You might
already
be able to do
declared.
that. I don't know. But I just think it's just like they don't have the keyword for each.
Okay, it's got to be a loop
Oh, it does.
variable.
Okay.
Yeah. That should be I'm quite a fan of the for each loops and wherever else we put that.
All right, cool. So we got 3 ways to do this, but really 2. All right. Questions on that? So you can do this with a linked list. You can do this with a list array, right? Performance issues, etc. A general comment on these in bold font. Note that this implementation is not synchronized. Most of these things that we're looking at are what we call not thread safe. Okay, they're not synchronized, meaning if 2 threads were to try to manipulate the same linked list at the same time, you might get into trouble. So imagine what your code does if you implement a linked list class and you're asked to delete a node. Right? You follow the pointers through until you get to the thing you want to delete. You take the previous node and you change it to point to the thing after the node that you're deleting. And imagine that at the same time, your code is running on the same locations in memory trying to insert a node. Right? You can see that if you set up the timing correctly, if you do a few steps of the deletion and then a few steps of the insertion and a few more of the deletion, you can get into this ATM, this Yoda Darth Vader problem of where you have inconsistent memory, and you can end up corrupting your list. You might be able to create a circular list, you might lose data, or truncate your list or things like that. So if you want to access most of these types of objects from multiple threads, you want to use the synchronized keyword and make sure you're controlling access so that only one thread is touching this thing at a time. And if there's a problem with that, it usually jumps out pretty quickly because you get all kinds of crazy stuff and it's slightly unpredictable. One exception to this is hash tables, because hash tables are synchronized. Yeah, I mean, it saves you a little bit of trouble. I also want to talk about this clone method. So most of these objects have the ability to be cloned, right? And remember, if you do something like this, so let's make an array list. So we have an array list called mine, and you construct it and you put some data in it and so on. And at some point, if you say this, second equals mine, and then you start doing things to this list, you're actually doing things to that list.
Oh, that's what it means by.
I mean, they're basically pointers.
They're pointers, right? So if you want to make a copy of this, right, there's a clone method, and you can say second equals mine.clone, and that will give you a copy, but it's what's called a shallow copy. So what's the difference between a shallow copy and a deep copy? A shallow copy will give you a new list. Okay, so you have a new collection of nodes. They have the same data in them. They point to each other in the same order and so on. But here's the difference. Right, so you make a copy, you've basically got two lists. But suppose that this is not just an integer. Suppose it's something more complex. Suppose it's a structure that's actually a word list. So you have a linked list of your word lists. Okay. So the data piece of this node is a thing that contains, you know, a list of nodes, where each node has a position list associated with it, and so on and so forth. Okay, it's an object. This is going to refer to the same object as this. So the list itself is a separate structure. I can delete this node and not affect this list at all. Okay, it's a copy of it. But if I modify this data, I'm going to also modify this data. If it's not something simple like an integer. Okay, if it's something that has its own, if it's its own instance of a class, right? So if you really want separate copies of the data that's up here in this structure down here, so you really have a completely separate, totally independent list, you want to do what's called a deep copy. And deep copies, more often than not, you end up coding them yourself, right? Clone will give you a shallow copy, but this is another source of potential mishap, because you build up a list or an object and you start manipulating what you think is a copy of it, and your original suddenly starts changing and you don't notice until something breaks.
When it says shallow clone, is it referring to the fact that it isn't the same list?
It's referring to the fact that it's not following. So the way I picture it is, here's your linked list, right? And from a top level view, here's a node, here's a node, here's a node. To make a copy, here's a copy of the first node, second node, third node, okay? But if you were to look deeper, right, this node actually contains something which has 5 fields in it, right? And each of those fields is itself some sort of data structure that has things referring to other fields and so on and so forth. And I've got that exact same structure here, right? Because I just said take what's in the data section here, put it down here. And I could clone it to make a copy of that, but if it's referring to things another level down, I need to go down another level to get that copy, right? So it's a harder thing to automate, a sort of full deep copy, and it's not always necessary. So if you need that, right, if you really want an independent list, go ahead and code it up yourself.
So clone will give you an exact copy that lets you manipulate it if it's a primitive data type?
If it's primitives, it should be fine. I'm not sure about strings. I'll have to write some code and try that. I'm also not sure when an equals sign actually invokes the clone method. So I'll cobble together some code and post that on Canvas. All right, shallow copy, deep copy. What else do I want to say here? All right, that's enough about lists. Let's talk about hashes. So you remember hashes from 222? So hash is this idea of an associative array. So we have a key and a value. And we store these things in pairs, right? So the key is kind of like an index into this associative array. We can say, tell me the data stored at index key, and it'll give us back whatever that data is that's stored there. So with an array, our keys are sequential integers starting at 0. In a hash, they can be anything. They can be strings, they can be non-sequential integers, they can be any type of object. So there's a multitude of classes provided for us. So one is a HashMap. Another is a hash table. And you can do a tree map, which is the best. So mostly we can say put a piece of data associated with a key, and then we can say get the piece of data associated with a given key. So that's the main store and fetch operations. But we can also do things like clear, and we can also say, is there an item associated with this particular key, and we can iterate. I gotta find the iterator.
Probably just get from entry set.
Just go on what?
From entry set. That would be the closest.
Yes. Okay. So we can get a set containing all the mappings, and then we can get an iterator on that set.
It's an interesting return value.
Yeah. Okay, and you can remove and other things like that. So hash table, basically the same. Main difference, hash tables are synchronized, hash maps are not, but hash maps allow null keys, hash tables do not. So if you want to store a null as a key, for whatever reason. And actually key set's the other way to get to an iterator. So key set gives you a set of all the keys, and then you can iterate on that. So these are generic, right? And you have two types of things. You have a type of key and a type of data, so you have to specify both of those. So let's do a hash table keyed on strings that stores strings. HashMap. There we go. So there's a hash map. So we can say map.put. And what should we do in here? Teaches. So there's a hash table of people and what course they're teaching, and if I do this, right, this is keyed off of that first argument. So the entry for Nick will be CSE 223. Okay, it's not like a regular collection or a list where you're adding nodes. We're indexing off of the name, so the data associated with the name Nick will now be CSE 223. We're overwriting. Okay, so different from a list. Say again? Right, right. So we can retrieve this two ways. We can put in a name and we can ask for what the data is, or we can use an iterator, right, if we want to see everything that's inside here. So my typing's on point today. So we can use the key set method, and that'll return to us a collection. So that's also generic, and that's one of the higher level sort of super classes for a lot of this stuff. So we get this collection C, and then we can just iterate. It doesn't like has next.
C is an iterator. It's a collection.
Yes. Oh. I gotta tell it what type I'm iterating. All right. So, map is our hash table, right? Our hash map. Key set returns a collection. So I'm setting C equal to the collection associated with the keys. So I declare it as a collection of type string. And then collections come with an iterator. So the iterator method will return an iterator, which I'm calling I, and I'm declaring to be an iterator of strings. And then iterators come with the has next and the next methods. So while the iterator has a next entry, we'll go ahead and call next, and we'll just print that out. And that'll give us a list of keys. And so if we run this, we just get a list of the names, the indexes into this hash map. But if we want to actually use that, then we can say, what did I call my map? Map.get, and we can get the key. So we'll get the next key, we'll store that in our string key, we'll print that out, and then we'll use that in the get method to see what's actually associated with that. And this gives you your list of the indexes and the data associated with them. All right, so that's the hash map. Hash tables are similar. And then there's a hash tree, which is similar to these, but it also alphabetizes, or it sorts your keys. Okay, so it's implemented as a hashable tree, basically. So you can pull data out in order according to whatever your comparator is. And when you construct a tree map, you can specify a comparator which says, how do I want to look at two objects of whatever type I'm storing in here and tell which one comes after the other. So for integers, it uses greater than, less than. For strings, it uses compare to. For other things, we can define what we want to use to compare. So maybe we want to sort in alphabetical order when you spell the word backwards. right? So starting with the last letter or something. We can specify a comparator and it'll use that. And again, it's a totally generic method. You can store whatever types of objects you want. And so you can use this to make a really nice version of PA2.
How would you say that? Like, what's the syntax for that? I guess?
For a comparator?
Yeah.
Um,
How would you want to turn something on?
more than 2 seconds.
Okay.
But you can click through on these, right? And you basically implement these methods, right? So we haven't talked about interfaces, but interfaces are sort of wrappers. They're sort of stencils you can use to create classes on your own. So you implement your own compare method that compares these two objects. And if you specify that as your comparator, it'll use that code when it's doing its which way do you go, left or right kind of thing.
So like you got two linked lists, and you want to not just check by first data point, you can figure that out with your own comparative method,
Yeah.
basically.
Mm-hmm.
Okay.
All right, so open lab tomorrow. Monday, I'll show you a version of PA2 using all of this stuff. I'll give you a preview. So there's PA2. And it's using a tree map, and the tree map is keyed off of strings, and the data type is an array list of integers. And all the hard work is done for you in these built-in classes. Right, so you can run this and it'll give you a nice index. And there's a toString method in these collections that print out comma-separated list of entries. So you don't even need to write that yourself. All right, so we'll play with that on Monday, and we'll probably talk about interfaces. And then we're going to start talking about binary trees, and we're going to talk about balancing trees. So we'll go over AVL trees, and we'll probably go over red-black trees. And tree maps use red-black trees internally, so that's worth going over. All right, so I'll see you tomorrow.